All right, today we're diving deep into a really groundbreaking paper from DeepMind. It introduces a totally new way of thinking about and building powerful language models. It's called Retro, and the big idea is that it learns by retrieving information from a massive database of trillions of tokens. So let's get into it and break down exactly how this thing works.
Here's how we're going to tackle this. First, we'll set the scene and talk about the fundamental problem that led to this research in the first place, this sort of scaling wall that AI is running into. Then we'll introduce the solution, Retro, what they call an open book AI. We'll peek under the hood to see the mechanics of how it actually looks things up, and then we'll get to the results, which are honestly pretty mind-blowing. And finally, we'll zoom out and think about what this new approach really means for the future of AI.
Okay, so let's set the stage. To really appreciate why RET is such a big deal, you first have to understand the world it was born into. And for years now, that world has been dominated by a single, simple principle. Bigger is better. This whole philosophy has kicked off what you could really only call an AI arms race. For a long time, the main path to getting better performance was just brute force scaling of model parameters. You can think of parameters as all the little internal knobs and dials the model has to learn from data. We've watched these models explode from having millions of parameters to having hundreds of billions. And look, this relentless growth has, without a doubt, led to some incredible new capabilities. Now, the researchers in the paper really pinpoint two main reasons why this scaling strategy works. First, pretty straightforward. More parameters means you've got more raw computational power to work with. But second, and this is absolutely crucial for our discussion today, it means the model can literally memorize more of its training data directly within its own weights. Those weights are just the learned connections inside its massive neural network. But this whole approach starts to beg a really critical question. Is this endless scaling really sustainable? Is the most efficient way to build intelligence really just to pack all of the world's knowledge into a model's internal parameters? This is the wall that the industry is starting to bump up against, and it's right here that our story really begins. So in response to this exact challenge, DeepMind introduces Retro. And what's important to understand is that this isn't just a small incremental improvement. It represents a whole new way of thinking, a semi-parametric approach. Now that's a bit of a technical term, but all it really means is that it combines a smaller, more manageable set of internal parameters with a huge external source of knowledge that it can tap into whenever it needs to. So what is Retro exactly? Well, the paper's official name for it is a retrieval-enhanced transformer. Let's just unpack that for a second. The key phrase here is that it conditions on document chunks retrieved from a large external corpus. To put that in plain English, it means that instead of trying to cram every fact it's ever seen into its own memory, it knows how to go look things up from a massive external library when it gets stuck. This slide here gives you the perfect analogy. Just think of a standard model, like a GPT-3, as if it's taking a closed book exam. It has to do all the hard work of memorizing everything, cramming all that information into its parameters before the test even starts. Retro, on the other hand, gets to take an open book exam. It has this enormous 2 trillion token external database, basically the ultimate cheat sheet, that it can consult in real time to find the best possible answer. It's a total game changer. Okay, so this all sounds great in theory, but how does Retro actually do this looking up? The mechanics behind this are both really fascinating and, frankly, incredibly clever. The whole process basically works in 4 main steps. First, any input text gets broken down into these small 64 token chunks. You can just think of tokens as words or even pieces of words. Then, for each one of those chunks, the system goes and retrieves the most similar text snippets, what they call neighbors, from its massive database. After it finds them, these neighbors are passed through an encoder to really capture their meaning. And finally, a very special mechanism integrates all of this retrieved information to help the model make a much better prediction about what comes next. Now, there are 2 key innovations that really make all of this possible. The first is the retriever itself, which uses what's called a frozen BERT model. And this is brilliant because frozen just means the search engine part of the system doesn't need to be constantly and expensively retrained, even as you add more data to the library. The second piece is something called chunked cross-attention. This is the real secret sauce here. It's the mechanism that lets the model elegantly weave that retrieved knowledge into its own internal thought process. So we've got this really elegant new architecture. But the big question is, does it actually work? Well, this is where the results start to get truly impressive. The headline number from the paper is just staggering.
Retro manages to achieve performance that's comparable to giants like GPT-3 while being 25 times smaller in terms of its parameters. It's a classic David and Goliath story. You have this much, much smaller model that, because it has access to a much bigger external brain, can go toe-to-toe with the titans of the industry. And this chart here really drives that point home. What you're seeing is a comparison between a 7.5 billion parameter retro model and the absolutely massive 178 billion parameter Jurassic 1 model. And on these complex benchmarks, you can see retro consistently outperforming the giant on datasets like books and even GitHub code. It's really remarkable. And what's more, the model's performance scales directly with the size of its external memory. As the retrieval database gets bigger, going from billions to trillions of tokens, the model just gets smarter. And this suggests a whole new way to improve AI. You just give it more reference material, more books for its library, without ever needing to make the core model itself any bigger. You know, perhaps one of the most practical and exciting findings in the whole paper is this idea of retrofitting. They show that you can take an existing pre-trained transformer model, freeze its original weights so they don't change, and then just bolt on these new retrieval components. This approach is incredibly efficient. It takes just a fraction of the original training data to create a model that performs almost as well as a retro model that was built from the ground up. So, when you step back and look at the whole picture, you realize that retro isn't just another new model architecture. It really signals a potential paradigm shift in how we think about knowledge and memory in artificial intelligence. This kind of approach has three massive advantages. First, it's way more efficient. It gives us a path to powerful AI without the insane computational and energy costs of just endlessly scaling up parameters. Second, it's updatable. To teach the model about a new event, you don't have to do a full, expensive retraining. You just add the new information to its library. And finally, and this is a big one, it offers a new level of interpretability. For the first time, we can actually see the sources a model is thinking about, which is a huge step towards making AI more transparent and, hopefully, more trustworthy. We'll end with this really powerful conclusion, straight from the authors themselves. They argue that this retrieval-based method isn't just another tool in the toolbox. They call it an orthogonal, more efficient approach to building powerful AI. So instead of just scaling up, we can now scale out. The question is no longer just how big is the model's brain, but rather, how big is its library? And that, well, that really changes everything.